Okay, lesson 52, absolute mins and maxes. So we've been doing a lot of problems, writing equations to find volume and area, and now we're going to use those equations and use our first derivative to help us find the maxes and the mins. Okay, first off, the first thing you need to remember is domain. You've always got to be thinking about domain in these real-life problems. All right, second thing, remembering our critical numbers. Critical numbers are when the slope is 0 or the slope does not exist. Now, the slope does not exist when you have corners or asymptotes, like an absolute value or something. That would be a corner. An asymptote would be when your equation does something like this. That's also a critical number. Now remember, this is f prime. It's possible for f prime to have an asymptote where the function does exist. The function does exist, but f prime does not. So when that occurs, that value of x is also a critical number. But if your equation is a simple polynomial with smooth curves, then you don't have to worry about it. All right, so my idea here is that I've got you thinking about domains, and the reason for that is because we have to think about endpoints. Let's say we have an x cubed. All right, you find this critical number and you find out that that's a max. You find this critical number and you find out that's a min. So you think this is your maximum area. But the problem occurs when your possible domain, say this is my x-axis, your possible domain is from here to here. When that occurs, then your maximum occurs at this endpoint. So when finding absolute mins and max, we have to think about not only when the slope equals 0 or when the slope does not exist, we have to think about endpoints also. This critical number has a slope of 0, and that is a local max, but the maximum, if this was an area, so say this was a of t or some a of x, then this would be your maximum area within those values of time, All right, so let's do a couple problems. Maybe it'll make a little more sense. I feel like I'm rambling. All right. Seen this before, haven't we? Okay, 100 yards of fence, rivers on one side. What's the greatest possible area? Okay, so let's think about this. 100 yards of fence, rivers on one side. So here's my river, here's my fence. I'm just going to call this x. So if this is x, this is also x. What's this? It's 100 minus 2x. So what's the area of that? It's x times 100 minus 2x. Well, let's talk about the domain. What's the smallest x could be? Well, in theory, x could be 0, right? You could put all your fence along the river and have absolutely no area, but that's the smallest x could be. What's the largest x could be? We'll see right here. If x is 50, 100 minus 2x is 0. So if x is 50, then I don't have any width. So x has to be greater than or equal to 0, less than or equal to 50. So that's my domain. So that's what I've got to think about. That's what I've got to remember. All right, so this is my area. Remember which color I was using. So a of x is x times 100 minus 2x. Multiply that out. That's 100x minus 2x squared. So how do I find when the area is maximized? A function is maximized when the first derivative is 0, right? So a prime would be 100 minus 4x. And when does that equal 0? So this equals 0 when x is 25. 100 is 4x, or x is 25. I guess I'm in yards. Yeah, 25 yards. All right, that's my critical number. That's not necessarily my maximum value. I have to go back to my original and say a of 0. Well, that's 0. My critical number, a of 25. This would be, let me see, I'll put it over here. 25 times 100 minus 50 is 50. 25 times 50, anybody got a calculator handy? 25 times 50 is 1,250. 1,250 square yards. Or, what's my other endpoint? My other endpoint is 50, and A of 50 is 0. So this provides your maximum area. The maximum area is when and we kind of already knew that because this is a downward parabola, right? The negative 2x squared. We knew that this value was going to give me the only max, but I need you to get in the habit of checking it. Check your endpoints for your domain and everywhere you have a critical number. Critical numbers are when the first derivative is 0 or the first derivative does not exist. All right, let's look at this next one. This next one's talking about find two positive numbers, not necessarily integers, okay? Find two positive numbers whose sum is 8 and provides a maximum product. Oops. Whose sum is 8 and provides a maximum product. All right, so sum x plus y is 8, and we want x times y to be a maximum. All right, remember we have to think about domain. What's domain? Well, the domain is going to be, it has to be positive, so 0 is less than or equal to x is less than or equal to 8. Well, 8 times 0 is going to give me a 0 product, so that's not going to be the maximum. But again, I'm focusing on this lesson, trying to emphasize domain. All right, so x plus y is 8. Therefore, y equals 8 minus x. Y equals 8 minus x. So my function for the product is going to be x times 8 minus x. That's my product with x. So 8x minus x squared is my product. When is a function maximized? When the first derivative is 0. 8 minus 2x equals p prime. So when x equals 4, p prime equals 0. So if x is 4, what's y? Y is also 4. X is 4, then y is 4. All right, so if I come up here and I find p of 4 is going to be 4 times 8 minus 4, so my product is going to be 4 times 4, 16. So my product then is going to be 16. So this is the maximum product, but we have to make sure we're answering a question. The maximum product is 16, but if they ask me what values provide the maximum product, that is x is 4 and y is 4. X is 4 and y is 4. The maximum product is 16. Now I haven't forgotten. We're going to go back here and check the other points. I kind of already did. If x is 0, what's y? If x is 0, that's one end of the domain. That means y is 8, right? Because x plus y has to equal 8. But x times y, the product of 0 is going to be 0. And so the product, if x is 8, the other endpoint, if x is 8, then y is 0. And again, the product when x is 8 is 0. So the maximum product is 16, and that occurs when x is 4 and y is 4. All right, last problem. This should look very familiar to you. Okay. We want the value of x, which gives the maximum volume of a box that's initially starts out a piece of cardboard that's 15 by 12, and we're going to make an open top box, and we want it to be maximum volume. Okay, again, you've done plenty of these, so I'm going to do this very quickly. Once I take an x off here and an x off here, my width, I keep doing that, my width is going to be 15 minus 2x. My length is going to be 12 minus 2x. And my height is going to be x. So that's my volume in terms of x. All right, let's talk about domain. What's my domain? Well, here I could take off 7.5, but here I could only take off 6. And I have to take off the same thing in both horizontal and vertical. So my domain is going to be x between 0 and 6. The maximum x can be is 6, because if I cut off more than 6, I can't cut into the other side. All right, so my volume in terms of x, let's see, so let's multiply this out. Change colors again. Let's multiply this out, and the volume in terms of x turns out to be, I've got it someplace, where is it? There it is, 180x minus 54x squared plus 4x cubed. So what's v prime? Well, when is a function maximized? A function is maximized when the first derivative is 0. So v prime is going to be 180 minus 108x plus 12x squared. I think there's probably a 6 in there. No, actually there's a 12 in there, isn't there? So rearranging this, factoring out a 12 times x squared minus, what is that, 9x plus 15, right, plus 15. Does this factor? No, it doesn't. Okay, this doesn't factor. Using quadratic equation, again, I put it in my calculator. 0 when x is, let's see, 2.2087 or 6.7913. So I have a possible maximum volume when x is 2.2087 or 6.7913. Okay, what's the first thing you see? What's the first thing you see? What's the domain? X has to be between 0 and 6, so this isn't going to do me any good. That's not in my domain. So my possible maximum volume is when v of 0, v of 2.2087, and v of 6. Right? Those are my possible endpoints. These are my endpoints, and within my domain, that's the value which makes the first derivative 0. Okay, so well, when I come back up here, v of 0, well, that one's pretty easy. That one's 0. Okay, and then I put the 6 in here. 12 minus 6, that's 0. It doesn't matter what these are. 0 times anything else is 0. So my maximum volume is going to occur when x is 2.2087. Now hopefully you're noticing, what did I do? I carried 4 decimal places here, right? I thought in AP Calculus we carried 3. We carry our final answer to 3. So this one needs to be at least 4 to solve the rounding. I always store it, all right? I copy this and store it someplace. So for example, I would call it A. I would take this value, just copy it off my screen, make it A, and then I would put into my calculator A times 15 minus 2A times 12 minus 2A, and that would give me a maximum volume of, what does it turn out to be? Maximum volume of 177.234. I believe this was inches squared, inches cubed. Gives me a maximum volume of 1.77234. Okay, as long as we're here, let's go ahead and look at v double prime. All right, let's look at v double prime. I could tell for sure that this is a maximum by taking v double prime, which is going to be, let's see, 124, well, 12 times 2x minus 9. So 12 times 2x minus 9, and when x is 2.2, v double prime of 2.2087, 2 times 3 is 6, so it's going to be less than 6 here. 6 minus 9, that's a negative. So v double prime is negative. Well, if v double prime is negative, therefore we have a maximum. So we've confirmed with our endpoints and the volume to show that this is the maximum volume. We've also confirmed using second derivative test that this gives you a maximum volume. Okay, happy thing.